In Notes 3.2, we're going to look at polynomial functions of higher degree. All right, a polynomial function, that's going to be a continuous, smooth, rounded graph, not like an absolute value function that has a sharp turn. So just as a reminder, because we've been working with polynomial functions, let's just consider the cubic graph, x cubed. Thinking about what we just read, these functions, polynomial functions, are continuous with smooth, rounded turns. An x cubed graph goes something like this. They're smooth and they have rounded turns. They don't have sharp turns. Alright, in this video we're going to be looking at characteristics of polynomial functions. That is, how do polynomial functions rise or fall as they come on a graphing screen and leave a graphing screen. For example, in this cubic function right here, the graph on the left falls, but the graph on the right side rises. So that's one of the objectives, is to describe the behavior of a polynomial function, meaning what's happening at its extreme left and extreme right. How does it rise? How does it fall? Alright, a leading coefficient test of a polynomial, and this is just generic form of a polynomial function. In our previous example of x cubed, a sub n would be the number 1. That's our coefficient. N just stands for a placement. Okay, a sub n just represents the coefficient. Our n, or our exponent, was 3 in the previous example, and we had no other terms, not even a constant, which a sub 0 without an x would represent a constant. So this is just the general form of a polynomial function. Any polynomial function, like a constant function that graphs as a horizontal line, a linear function that we're familiar with, a straight line, with or without a slope of 0. A quadratic is a polynomial, a cubic, a fourth degree, fifth degree, etc. And degree again means exponent. Alright, so let's look at some characteristics of these polynomial functions. When n, or the exponent, also called the degree, is odd. Okay, what can we expect of the ends of the graph? Well, we have to consider two things. Okay, if I have an x cubed graph, what's the coefficient, or a sub n's value? Is it positive? Because with our previous example, a sub n was 1, it was positive with the third degree function, or 3 being odd. Okay, what does the behavior of the graph at its ends look like? Okay, so we'll just draw a representation when n is odd and a sub n, or the coefficient, is even. Well, an odd function, when a sub n is greater than 0, would look something like this. If n is odd like 3, or n is odd like 5, or n is odd like 7, 9, etc., and the coefficient a sub n is positive, the graph will come on the screen from bottom left and leave top right. So the description of the behavior is this. Falls left, which that means in notation that as x approaches, that's what that arrow is, approaches negative infinity. As if I start right here and I travel to where x is negative, okay, the y values are going down further to negative infinity. Y would approach negative infinity. That's a description of the behavior on the left. Now let's look at a description of the behavior on the right. Well, in this situation, when we have an odd exponent but a positive coefficient, the graph is going to rise, that should be rises, to the right. So it's rising as we leave the screen to the right. Okay, what's the notation? Well, as x goes to infinity, the y's are also going to larger numbers, infinity. So as x travels to positive infinity, the y's would also go higher and higher. All right, well, let's look at this case. There's 4 cases. We've looked at one. Let's look at the second one. When n is odd, but the number in front of that term is negative, we're going to have a situation such as this. The ends of the graph go in opposite direction, but the graph comes on the screen this way and leaves the screen this way. So the description is that the graph rises left, you can see, and falls right. So let's look at the left situation first. So it rises left. So the notation is, as I move left to negative numbers, as x approaches negative infinity, the y values of the points on the graph go to positive infinity. The behavior on the right falls right. The notation is x goes to infinity, y goes to negative infinity. X goes to bigger numbers, positive, y goes to negative numbers. We've just explored the case in the description of a polynomial function that has the highest degree or highest exponent that is odd. Now we have to look at the other half of the cases when the highest exponent is even. Right, so when n is even, we want to consider whether or not the coefficient is positive or negative. So let's look at an even polynomial. And it's easy to kind of think of a quadratic as well. Okay, if I have a quadratic or a 4th degree or a 6th degree, but the coefficient on that highest term, or highest degree term, is positive, it's going to look something like an upward opening parabola. It might have a few bumps along the way, but both ends are up as opposed to one down, one up when a sub n, or the coefficient, is positive. So what's the description of that behavior? Well, we can see rises left and rises right. All right, the notation to the left would indicate the x values are going to negative infinity, and if it rises, then the y's are going to positive infinity. So if I go to negative infinity and I jump on the graph, the y's are always getting bigger. Likewise, if x travels to positive numbers this way and I have to jump on the graph, the y's are also going to positive infinity. And the fourth and final case, considering when n is even, if the coefficient, the number in front of that term, is negative, think of a negative x squared graph that opens down, or a 4th degree or a 6th degree. Both ends would be down. So we fall to the left and we fall to the right. The description of falls left, x goes to negative infinity, y goes to negative infinity. Falls right, as x goes to positive infinity, y also goes to negative infinity. So that's how we're going to describe the behavior of a graph. Oh, before I move on, let me come back over here. I should have put rises right, which to the right means x is approaching infinity, and rises means y is going to positive infinity. All right, let's look at some examples. Okay, so in your homework you're going to be asked to describe the behavior of the polynomial function. So we want to look at this as n is the highest exponent, n is odd, and a sub n, which equals the coefficient, happens to be -1, which is less than 0. So looking back at our 4 cases, when n is odd and a sub n is less than 0, okay, if you wanted to draw a picture of that representation, you could draw it like one of the like the one that was given previous in our previous example. You could. Otherwise, we just have to know what the basic shape of the graph looks like so that we can describe the behavior, okay, using this kind of notation. Again, a graph might help you. If you don't need a graph, that's wonderful. But when n is odd and the coefficient is negative, it's going to take on this basic shape. So the graph rises left and falls right. So I mentioned stating the notation, but in this case, let's just do a description without the notation. So let's look at example 2. N is odd, but a sub n, which equals 2, a sub n represents the a value, I guess if you want to call it that, that's positive. So looking at our previous examples up above, if n is odd, but the coefficient is positive, the graph is going to have this basic shape at its far left and far right. So it falls left and rises on the right. So it's just actually a matter of memorization. Let's look at example 3. N is even, it's 4. A sub n is positive 1, which is greater than 0. If the highest exponent is even, it's like an upward or downward opening parabola. If a sub n is positive, behavior of the graph looks like this. So to describe the behavior, it rises left and rises right. Example 4, n is even, it's 4. A sub n is negative 5, which is less than 0. Even highest exponent with an odd coefficient would look like this. Falls left, falls right. In the next video, we're going to look at more characteristics of polynomial functions.